This is the final session for today's event, and I want to invite Tom Gibbs and David Hall to talk about, to talk about recent breakthroughs that have been enabled by artificial intelligence. So please, Tom, take it away.
So the opening question that I have, David, did you want me to start or did you want to start?
I'll go ahead and start if that's what you want to do.
Sure, that's fine.
So hi, my name is David Hall. I'm a senior data scientist with NVIDIA. So in this presentation, I'll be discussing deep learning and how it's being applied to weather and climate research in particular. So as you've already seen, deep learning is just one of several approaches which allows us to take advantage of NVIDIA's GPU acceleration. But in my opinion, deep learning is a particularly powerful approach, as it allows us to build next level software that just can't be built in any other way. Over the past couple of years, deep learning has begun to have a really big impact on the Earth system sciences. There's quite a lot to know about this subject, but over about 20 minutes, I'll try and do my best to summarize the latest breakthroughs and developments in this area. Then Tom will take the wheel and discuss applications more broadly for science, I believe. So let's quickly review how deep learning fits in with high performance computing and GPUs. I think most of the people listening are probably aware that GPUs are an increasingly important resource for high performance computing. In recent years, their performance gains have outpaced those of CPUs, and there's a lot to be gained by building machines packed with GPU accelerators if we can use them effectively. They're also more power efficient, which can reduce the power bill and the environmental impact. We can quantify this assertion if we look at NVIDIA's recent results on the TPC-XBB Big Data Analytics benchmark. This benchmark, traditionally run on CPU-based systems, contains 30 use cases simulating big data processing. In June of this year, NVIDIA used a server with 16 DGX A100 systems to run the benchmark in only about 14.5 minutes, which was nearly 20 times as fast as the previous best result. So if you wanted to achieve the same performance, it would require about 350 CPU servers. So this benchmark shows that NVIDIA GPUs are able to perform big data tasks at about 1/7 the cost while using 1/3 of the power. There are a lot of ways one can use GPU accelerators. The low-level approaches that we've discussed include things like OpenACC directives or building custom CUDA kernels. High-level approaches include using domain-specific languages like Cyclone or performance portable libraries like Cocos or Claw if you're in the weather and climate areas. Deep learning provides another high-level path to GPU acceleration that's complementary to, but very different from, the other approaches that I've listed here. In contrast with the other approaches, not only can deep learning enhance and accelerate our models, it can help us to build new capabilities that can't be built in any other way. So in case you don't know, or you don't remember, deep learning works by reverse engineering functions from a large set of examples of how it should behave. It's basically a generalization of curve fitting, but in very high dimensional spaces. For most purposes, deep learning is probably best thought of as a new and powerful way to write software with its own unique set of strengths and weaknesses. Like traditional software, deep learning also builds functions, but it reverse engineers them from examples. The functions built in this way can be just as powerful as those built by hand, and in many cases, it can be much more so. Not only is deep learning able to build next level capabilities, and this software written in this way is automatically optimized for the GPU. This allows us to take full advantage of our hardware acceleration without manually porting code or maintaining multiple software versions. The field of AI changes really quickly, so the main goal of this presentation is to give an overview and a snapshot of the rapidly moving frontier of AI as applied to the Earth system sciences. So to do so, I'll survey some recent applications, examine progress towards overcoming scientific barriers, and take a look at promising new hardware and software tools. So let's start by looking at some of the recent applications. Before jumping into the specifics, I'd like to point out how rapidly this field is changing. Over the past couple of years, large segments of the geoscience community have begun to embrace machine learning and deep learning. Hundreds of scientific applications have been built, and most major institutions in this area have begun to develop focused AI programs. The US federal government is taking AI very seriously and has recently announced funding for 7 AI institutes focused on accelerating its development in various fields. Of these institutes, the one most relevant for this talk is the NSF AI Institute for Research on Trustworthy AI in Weather, Climate, and Coastal Oceanography, which NVIDIA also supports. NOAA is also taking AI very seriously. In February of this year, they published their official artificial intelligence strategy document, established an advisory board, and began to compile funding and personnel for a new NOAA Center for AI. Many science-based organizations across the globe are making similar investments. One important AI application is emulation, which has the potential to become a game-changing technique. Emulation uses deep learning to build fast GPU-accelerated surrogate models for expensive calculations. For very expensive routines, it can achieve a speedup of orders of magnitude. So far, however, emulation has yet to reach its full potential as it's still very new and it has several technical challenges that are yet to be fully addressed. We can come back to those in the next section a little bit. Despite these challenges, there have been some recent successes in the use of model emulation. For example, researchers from the Oak Ridge National Laboratory trained a neural network to emulate shortwave and long-wave radiative transfer calculations in the super-parameterized version of the E3SM Earth system model. By doing so, they were able to speed up these calculations by about a factor of 10 while maintaining high accuracy. Deep learning can also be used to build improved physical parameterizations for your models. As an example, in their 2020 paper in Nature Communications, Yanni Aval and Paul O'Gorman of MIT demonstrated how to build a more accurate parameterization of the global atmosphere. They used a random forest to learn a parameterization from coarse-grained output of a 3-dimensional idealized atmosphere model. And this parameterization led to fast, stable simulations that faithfully replicate the climate of the high-res simulation. Another useful application of deep learning is model bias correction. Researchers at NVIDIA, including myself, are working with ECMWF to build a neural network that removes persistent patterns of bias in the IFS weather model. The plots at the bottom show that the prototype networks are producing accurate bias predictions and that these can reduce forecasting errors. So far, we're seeing good results in an offline mode and are working to figure out how to best apply this correction in an online in situ in the model fashion. While deep learning can improve existing models, there's a growing list of use cases where data-driven solutions are actually able to outperform physics-based models for certain tasks. One such task is nowcasting. In 2020, Google Research published a paper on a method called MetNet that was able to produce significantly more accurate precipitation predictions out to 8 hours relative to NOAA's 3-kilometer high-resolution rapid refresh model. While MetNet established that deep learning can perform well at nowcasting, it still remained to be seen if data-driven models were able to tackle medium-range forecasts, which span days rather than just hours. To address this question, Stefan Rasp and collaborators constructed a new benchmark called WeatherBench, which provides a dataset and well-defined metrics for success, allowing easy intercomparison of data-driven approaches. The data is sampled at a resolution of about 5.5 degrees in the horizontal to keep its size manageable. Having established this benchmark, Rasp and colleagues published a second paper where they constructed a deep learning model to solve it. In this case, they trained a series of ResNet models with 19 residual blocks and found their performance to be comparable with the predictions made by IFS simulations at similar resolutions. In other words, the authors observed that our results indicate that given enough training data, data-driven models can compete with physical models. Another remarkable paper published in Nature demonstrates a deep convolutional neural network was able to predict the future state of the El Nino Southern Oscillation out to 18 months in advance, with a far higher correlation skill score than the current state-of-the-art dynamical forecast systems. As with the other successful approaches described thus far, transfer learning from historical simulations was critical for overcoming the limited availability of observational data. Another important application was described in GRL in August of this year, where researchers combined expert knowledge and machine learning to improve the prediction of rapid intensification of tropical cyclones by as much as 200% over the current operational consensus. This is particularly relevant and important this year, considering the record-breaking hurricane season we've been having and still are having. Chris Kadow, Uwe Ulbrich, and myself published a paper this year in Nature Geoscience that uses NVIDIA's inpainting technique to fill in missing climate data. Historical observations can be very sparse, especially in the distant past. But using transfer learning, we were able to pre-train an inpainting network using reanalysis and climate data. After training, the network was able to reconstruct missing observations from the HADCRUT-4 climate dataset, resulting in a more accurate reconstruction of the global historical temperature record as far back as the year 1850. So now that we've looked at some of the most recent applications of deep learning in the earth sciences, let's take a look at the progress being made toward overcoming AI scientific challenges. So while the power and utility of deep learning is pretty much undeniable, there are additional considerations that need to be addressed when you apply it to science. Learned methods should be accurate, but also trustworthy and explainable, and they should enforce physical constraints when appropriate. Researchers are hard at work addressing these issues and a number of other issues also listed here. One issue with systems discovered automatically from data is they often don't strictly enforce known physical constraints, like conservation of energy, unless they're explicitly designed to do so. Several techniques are available to accomplish this, including loss function penalization and explicit encoding of constraints in the model. Enforcing physical constraints has been shown to increase the accuracy and generalization of the model while decreasing its data requirements. A highly cited example of this was published in 2019 by Karniadakis and collaborators, in which they addressed two classes of problems using physics-informed neural nets. In the first case, a neural net represents the solution to a partial differential equation, which is hard-coded in the underlying framework. The figure on the right shows an example using Berger's equation. The initial and boundary conditions are specified, and the neural net describes the solution on the interior. In the second case, a set of physical constraints are treated as unknowns, and they are reverse engineered from a sparse set of observations. This approach allows both discovery of the PDE coefficients and description of the solution throughout the domain. NVIDIA's SimNet is a new tool introduced at the GTC keynote last spring that provides a set of tools to make physics-informed neural networks easier to use on NVIDIA's GPUs. You can apply for early access if you'd like to try it out. And you can watch the keynote if you want to see more details about that. Another problem with functions built by deep learning is that they never throw exceptions. In other words, they'll always return an answer, even if it is wildly incorrect. Typically, learned models are only accurate in the neighborhood of the training examples. To overcome this, we need networks that return both answers and error bars. Several methods have been developed for estimating both epistemic error, which arises from a lack of training data, and aleatoric error, which is the inherent noisiness of our samples. Techniques for quantifying error include Monte Carlo dropout, deep ensembles, ensemble averaging, dropout ensembles, and Gaussian process inference, amongst others. Of these techniques, Gaussian process inference gives the best results, but it just doesn't scale well. The next best solution is produced by deep ensembles, which are also able to distinguish between the two sources of error. When using a neural network emulation, epistemic error estimates can tell us when we've strayed too far from our training data. When that happens, we can fall back on the original calculation and later incorporate these new data points for model fine-tuning. The same thing that makes deep learning powerful can make it difficult to understand. Namely, can develop complex, subtle, and highly redundant algorithms that are very hard for a human to decipher. Nevertheless, it's often important to understand how the network made a decision. Some leading solutions for this problem include layer-wise relevance propagation, saliency maps, and local explanations. An article published this summer by Ben Toms and his colleagues at Colorado State show how layer-wise relevance propagation and backwards optimization may be applied to a neural network trained to distinguish El Niño and La Niña phases of the Southern Oscillation. This paper shows how these methods can help visualize what the network has learned, and they have the potential to facilitate scientific discovery from data. Another important technique in this area is called the LIME method, which stands for Local Interpretable Model Agnostic Explanations. This technique is able to explain the decision of any classifier by constructing a local approximation of the classification boundary. This allows one to build a defensible explanation when using a neural network to help in important decision-making. A major barrier for many Earth system models is the fact that the HPC components are written in FORTRAN, but the most popular and useful deep learning frameworks are written in Python. Unfortunately, while there are many potential solutions to this problem, none of them yet are truly ideal. My favorite personal solution is to use the Julia language for both components or as a wrapper for FORTRAN. MXNet is a good solution if your model is built in C++. The FORTRAN Keras bridge is a noteworthy attempt to overcome this barrier, but it's currently limited to dense networks. A neural net framework written in native FORTRAN might be a good solution, but so far this option hasn't achieved a critical mass. Perhaps the best solution would be a set of FORTRAN bindings to PyTorch or TensorFlow. However, this solution has also not yet been implemented in an open source fashion, although people are looking at it, including us. A problem that plagues many trained neural networks is that of output smoothing. That is, when training a model, the output often appears smoother than the original training data. Why this happens is easy to understand if we look at temperature forecasting as an example. Given a set of initial conditions, the forecast is chaotic and uncertain, leading to many possible ensemble members shown here in red. If we train a neural network to predict a single temperature curve, the best it can do is to predict the ensemble mean shown in black. Since it represents an average, it will never produce the same maxima, minima, or internal variation as the ensemble members. So how do we overcome this problem? What is required is a generative model that can generate new members. David John Gagne and his co-authors recently built such a stochastic parameterization for the Toy Lorenz 96 model. In their paper, they trained a generative adversarial model to produce predictions stochastically. The paper shows they were able to produce realistic predictions and that the machine learning models in some cases produced forecasts that were more accurate than handcrafted stochastic parameterizations. So in this last section, I would like to examine some of the hardware and software tools that have emerged that are likely to have a major impact on climate and weather applications of deep learning. First and foremost, of course, is the most recent generation of GPUs from NVIDIA. This new architecture manages to produce optimal model training and inference performance in a single device, so you don't need different GPUs for each one. It doubles HPC throughput and gives a 20x boost to AI applications. It has hardware support for sparse neural nets and allows you to split the GPU into 7 instances to share amongst researchers. If you saw the GTC keynote in the spring, then you saw OMNIVERSE. It combines interactive ray tracing and physical simulation across many popular applications. OMNIVERSE has the potential to produce amazing real-time ray-traced visualizations of scientific data. In these very early examples, you can see renderings made by linking the ParaView application with OMNIVERSE. Here, renders are shown using 1.4 kilometer IFS model runs generated by the Summit supercomputer. And for many users of PyTorch, I highly recommend the new tool PyTorch-LIGHTNIng. It allows you to take advantage of many powerful techniques for accelerating model development and testing, such as multi-GPU training and reduced precision training. It also helps build standardized, reproducible code, which is why it's recommended by the NeurIPS PyTorch Reproducibility Challenge. And an expansion of PyTorch called PYTORCH-LIGHTNING BOLTS just came out in September of this year, and it provides a wide array of state-of-the-art models for you to use, giving you easy access to many of the breakthroughs and advances that I've been discussing in this talk without having to do a lot of model development yourself. So in summary, deep learning is a new and powerful approach for building GPU-accelerated software. It gives GPU acceleration basically for free without explicit porting, because it's all automatically accelerated. The geoscience community is making rapid progress with these tools, and data-driven approaches can, in some cases, exceed the capabilities of traditional simulations, which would surprise some people. The power of deep learning is growing really rapidly, and it's likely to be a very important component and driver of scientific applications for the foreseeable future.
So I'm Tom Gibbs, and I manage developer relations for the HPC business unit at NVIDIA. And what I'd like to do today is kind of pick up where David left off and drill into some specific examples, although he did a pretty fine job at digging into some for weather. What I want to key on today are those applications of the AI method which are integrated very closely with conventional HPC algorithms and application development. And the focus that I want to drill into is combining these two methods to address grand challenge problems where quite likely HPC on its own would struggle to achieve either the accuracy or the time to solution, particularly at the scale for the problems that are required to address grand challenge problems. The first grand challenge problem I want to dig into, and I'll go through a couple of examples, is fusion power. And as David talked about hurricane season, I believe with one more hurricane, we'll have the most, the most climate events of that nature in US history. And if not, I think we're tied right now. And so the issue of global warming is one that I think is becoming pretty well understood, at least tactically here. And one approach to addressing that would be fusion power. And there's an experiment that's being built in France called ITER, which is intended to do a proof of concept that would ultimately lead to commercially viable fusion. I think the target date that they're aiming at for the ultimate commercialization would be like 2035, and ITER goes online in the late 2020s. There are a number of challenges with ITER, and one of them is managing the plasma flow as it circulates inside of the tokamak. Now, when this happens, and the edge effects of the plasma, there are disruptions. And there are multiple HPC codes that have been written to simulate this effect. Probably the leading one is XGC, which is developed at the Princeton Plasma Physics Lab. It runs on all of Summit. It's an exascale application. But as they got closer to looking at ITER, they realized that there'll be 40 species of tungsten inside the walls of the experiment. And the operator that they use to model the interaction between the plasma disruptions and the tungsten wall scales by n squared. And this is one of the classic scaling problems you have with HPC codes. As accurate as this is, there's no way they'll be able to scale it by 160x. So what would typically have to be done in an HPC, classical HPC sense, is some form of reduced order model. What they did with some folks at Argonne is took the Fokker-Planck model operator out of the XGC application and trained a surrogate for that part of the simulation with a recurrent segmentation network. And I'm going to dig into this on the accompanying slides. And they demonstrated that they could provide equivalent accuracy, which is 10 to the minus 5, as that they could get with the HPC app. But the inference net it looks to be at least 100 and maybe greater than that faster, and then would be able to scale linearly as opposed to by n squared. So there's still work to be done. I think the paper on this was just published or hit archive actually in September. Let me dig in a little bit to what they did. So you may have simulations similar to this where you've got functions that look similar to the Fokker-Planck Landau model. What they did is they created a surrogate, and I think it's interesting that they applied a recurrent segmentation network. One of the challenges we have in using AI for science is that many of the AI models are built for vision problems, and in most cases the vision problems aren't dynamic, and in this case the ultimate physics are dynamic. They're changing with time. So what the segmentation network does is it combines, shown here a bit on the first few layers on the left, a classic CNN, so convolutional neural net, with a recurrent neural net. So it's kind of a combination of the two approaches. As they tested the different network types, this was the one that gave them the most resiliency and the best accuracy. But what they found is that, and David mentioned physics-informed neural nets. So one of the most straightforward ways to address physics constraints is to apply a fixed penalty, where this equation on the top is stochastic gradient descent, and the equation on the bottom is the conservation of mass, mass and energy. And essentially what they found is when they applied the fixed penalty a method, on the left, you can see the error, this loss, gets down to about 10 to the minus 3. And as you look to the right, you can see the fixed penalty is better than the unconstrained model. So what they did is they tested stochastic gradient descent, or SGD, by itself. Then they applied the fixed penalty. The fixed penalty is better, but it was not good enough. So what they did is they applied an augmented Lagrangian method, and that's shown here. So this is an extra term. And essentially what they're trying to do here is get past the appearance of local minima and maxima as they go through the loss function. And without going into the details here, essentially what's done is the loss function of the deep neural net is augmented with this kind of if-then-else approach to, which loss they want to use, and they combine it when necessary. And by augmenting the loss function, they're able to move the accuracy from 10 to the minus 3 to almost 10 to the minus 6. And you can see then that the stochastic Lagrangian relative to the fixed penalty is about, almost 2 to 3 orders of magnitude better. So what's not shown here, if we took the stochastic gradient descent, went to fixed penalty, you get about 3 orders of magnitude improvement, and you go again, you get another 3 orders. So what's shown here, I think 2 things to take away. There's more than one network type that you can use, and more than one way you can approach the loss function. And by applying these novel techniques, they were able to generate some very impressive results, which would be a step along the way to creating models that would be worthy of the ITER experiment. The next challenge you have with an experiment of this magnitude is housing the plasma. So for those folks that are familiar at all with fusion, kind of the link between fusion and climate weather is that the plasma inside the tokamak gets about as hot as the sun. So that's one of the reasons the disruptions are so problematic. And in this case, you've got to design a housing that can withstand the disruptions, the occasional disruptions when they happen. And what's shown here is what the inside of what the tokamak looks like. The challenge you have is that, and you see this in biological modeling as well, the methods in conventional HPC approaches that can accommodate models with large enough scale, so enough atoms over a long enough period of time, generally are less accurate than is required for this class of experiment. The alternative methods in HPC that are highly accurate, in this case, they'd be referred to as density functional theory, are incredibly expensive. And as you try to increase the scale from maybe 100 atoms to 1,000 atoms, and the time scale from maybe 10 nanoseconds to a millisecond or a microsecond, the methods become much less accurate. So what was done is at Sandia was to take LAMPS, which is a molecular dynamics code, and augment it with SNAP. So in this case, they kept the scale and the time dissolution of LAMPS, but augmented the accuracy by interjecting a machine learned potential inside of the existing application. What's shown here is the increase in test error capability. So in this case, lower is better. And SNAP and GAP are 2 brand new methods. Also, this slide also shows when the methods were developed. So Leonard Jones was which I don't think is even shown on here, which is LJ in the upper left, I think actually goes off the chart down to the left. It's about 100 years old. It happens to be well used and it's accurate enough for many things, just wouldn't be accurate enough for the ITER experiment. So what they did is they trained a machine learned model with a modified version of SNAP, and it included some of the capabilities with a gap, which is the Gaussian approximation potential. Details are given in the accompanying papers, and what they were able to do by embedding this module inside of lamps is generate accuracy. Actually, in this case, maybe better than the DFT. So what we're showing here is the energy barrier as a model with SNAP as the red line, DFT would be the blue, and you're now able to run this problem at the kind of scale that is conventionally done with lamps and get the performance in terms of accuracy that you'd be able to get with a DFT simulation. I want to stop here for a second and go back to something David mentioned. Both of these applications were written in C++. So while embedding PyTorch or the Python inference engines that come out of the training into the main application, it's not trivial, but it's certainly doable, and the tools to do that are already available. I'll also say that the XGC application was originally written in FORTRAN, and for multiple reasons, the development community for XGC just in the last couple of years converted it to C++, and they did that for a couple of reasons. But one of them was so they could be ready to embed some of these machine learning capabilities. And if you happen to be a developer that is working with an existing FORTRAN code, this might be something you would need to consider. So in the case of solving the grand challenge problem, there are two things we need to address in the modeling. One is how we can get the plasma and how we model the plasma inside the reactor, and then the reactor chamber itself. Now, once we've got the plasma moving and we've got the plasma generating heat, it is going to disrupt. And what we need to be able to do is model those disruptions and then be able to control the experiment to try to alert ourselves that the disruption might happen and adjust the experiment to either reduce them or eliminate them entirely if possible. The conventional methods to do this were tried. Support vector methods, so some of the conventional machine learning methods were applied to this problem. The challenge was that they were very experiment specific. So going across from one experiment to the next, it was really difficult to get the conventional machine learned models to be robust enough, and they weren't accurate enough. Team at Princeton and Harvard, along with some folks at NVIDIA, started down the path of applying a recurrent neural net that they developed. I'll give you a brief peek into that. And they trained and validated that against the conventional method, and the initial look at the FRNN is very good. By no means are we there yet. This work is ongoing. In fact, in each of these three examples, in fact, everything I'll be talking about, I'm giving you a snapshot that's probably a few months old, and all of these research projects are ongoing. In this case, this is what the FRNN looks like. The two things they're trying to balance are the probability of false alarm and the probability of accurate detection. So they want to detect that a disruption is going to happen, do it far enough in advance that they can react to it, and then avoid the probability that in fact the alarm was false, in which case they would have adjusted the experiment and it didn't need to. So what's shown here is the combined accuracy. This table may be a little bit complicated to read. D3D is actually an experiment that exists in that is running in San Diego, and JET is the Joint European Tokamak, and it's housed in the UK. CW is the carbon wall model, and ILW is basically a modified model that would represent ITER. That's what ILW is. Deciphering the net for the best classical method was able to beat FRNN with 1D if it was just on one experiment, but with the combined experiment, really nothing was close. You were almost about 5 or 6 percentage points away better with FRNN, and 0D is using 0-dimensional data that comes off of the experiment, and 1D is using 1-dimensional data that comes off of the experiment. The next steps in this this evolution are to begin to get higher order dimensions of data. The other is that when we look at these types of prediction problems, the classical methods are generally hidebound to be a first-order Markov process. It's not clear that the statistics actually behave that way. Research team at NVIDIA, I think LU, some of this method was briefed at the AI Center here either earlier this week or last, are exploring a method that's referred to as hot tensor or higher order tensors. And this would give you the ability to adjust the LSTM here in the neural net so that it could comprehend more than a first order, maybe second order Markov process. And this is really computationally prohibitive with classical methods and could open the door to being able to balance the challenge between probability of false alarm and probability of accurate detection. So these are things that are ongoing right now with this research. I'll close with an example that'll be close to home for some of the folks in NCSA U of I, and that is a composite workflow that was developed and actually, I don't want to steal the thunder, but submitted as part of the Gordon Bell for COVID-19. In this case, the challenge I think everybody's pretty well aware of. This virus is pretty darn complicated, and coming up with drugs that are either going to directly address it and or a vaccine is clearly at the front of probably everyone's mind. And let's just say it's a really hard problem to solve. One of the challenges you have here with the biological model is similar to the one we had with the materials model, which is the classical methods that we use have this sort of yin and yang. The ones that are big enough that can look at a big enough model over a long enough period of time, generally don't have the same level of atomic accuracy as the quantum chemistry methods. And when we start to look at models that are big enough to simulate, the spike protein and the full membrane, these models get really big, and they're very, very expensive. So what was done here is to combine actually a couple of things that were discussed today. This workflow actually combines Autodoc. So if you recall in Zara's talk, we were describing Autodoc and the work that was done on Summit to improve the performance. So this takes Autodoc GPU, tunes the input to the Autodoc GPU to derive drug candidates. Those then are filtered. This is basically it uses the AI method in this upper right-hand corner to filter the output of the Autodoc and the conformational structure of the protein. That data is then input to the bottom right, which is a workflow referred to as Deep Drive MD. This is an application that was developed by some folks at Rutgers and Argonne. Essentially here, what's done is to run molecular dynamics simulations in an ensemble way. The ensemble is filtered with a convolutional variational autoencoder. The CVAE is trained with the data from the autodocking process. So once the data it's trained, then we can test and try different things with a molecular dynamics simulation to see if we can't fine tune what's happening at the spike. Once that data is run, this ensemble is run, then that information can be passed over to the multi-scale, multi-resolution model. And in this case, that multi-scale, multi-resolution model happens to be one pretty close, was developed pretty close to home. It's NAMD. Let me just draw these workflows on here. Oops. Essentially here, what was done with NAMD, conveniently the work that we've done with the folks at U of I and NCSA over the last decade had that code in the position that starting in late September, effectively from almost scratch, the team was able to get an application, we believe is probably the largest molecular modeling run ever done on Summit. It's 300 million atoms over about 30 nanoseconds. It was a tremendous achievement, and without the work that has gone on over really the last 10 years, it would have been impossible. In fact, we were very fortunate that between Oak Ridge and NVIDIA and NCSA, they were able to actually get us kind of an updated version of NAMD that had special features to run extra large models, and that happened to be ready to go for us to do this workflow experiment. So this is still work ongoing. The ability to actually steer the simulations, to basically steer the ensemble in the bottom right with data from auto docking in the upper right, and then take that and further steer the large scale simulation is we did an early proof of concept. This is work that will be ongoing, but it demonstrates some exciting potential for us to be able to do much more accurate and robust models for some really important problems, because clearly having something like this ready to go will have us ready for the next pandemic. And with that, I'll close. In this hopefully era of unity, I'll use a quote from the founder of one of our competitors. It's one of my favorite quotes. Don't be encumbered by history, just go out and do something wonderful.
That's great, Tom. Thanks a lot for the presentation, and to David as well. Any questions from the audience? So, Tom, one question for you. Based on the trends that you are observing with new applications of AI, where do you see the most impactful or fastest growth for the next few years?
Well, that's a really open-ended question. The trends that I'm seeing, and I think David's seen the same thing, the FRNN model that was done, I showed there with pop out of this, with Dr. Tang and company at Princeton, was a pretty relatively simple model. And if I'm looking at the model that was done to model the Fokker-Planck, was much more complicated. If I look at the model that Dr. Tang and company are doing with Anima and Kumar at NVIDIA, much more complicated. So I think the trend I'm seeing in the very near term is that the models that will be contemplated are going to become much more complicated, and I think that and bigger. I'm afraid I may have. Did I lose everybody here?
So do you think that people will try to incorporate some domain knowledge into the construction of the networks to try to do this in a more efficient way or in a clever way? Because you can go very deep. And I think Resner gave us some insights about this, that sometimes you can go deep, but that doesn't give you the best performance, right?
Sure. I mean, when I say complicated, that doesn't necessarily mean deep. It just means that they're probably not as simple. I think the example with XGC, where they use the Lagrangian augmented, the Lagrangian augmentation, as an example where, so first of all, if you look, they applied the SGD and they got one level of accuracy. Then they applied a fixed penalty physics-informed neural net. That would probably be the way, when most people think of PIN, that's what they're thinking about. I'll give a fixed penalty if the loss starts to, if the conservation of mass isn't obeyed. right? Very the simplest approach. And it was better, no doubt, right? You got better, but it wasn't good enough. So they then, the Lagrangian method basically is a more sophisticated approach to avoid getting sucked into a local minima or maxima that isn't, representative of the overall statistics. And so, that was the first time, honestly, I'd seen anyone apply that approach to the loss function. And I would expect that there will be, people will put. I expect there'll be a lot of more experimentation in that direction. To the point David made, I think, when he kind of said, "What are the issues?" One of them is trust, and being able to inform the loss function with physics, I think, is one way to help embed the trust. The other, I think, is embedding the neural net or coupling it with the existing well-understood HPC simulation, and we have 40 years of history using those. And the closer that it's coupled with that, so people see that it, in some levels, it just isn't. I just trained this network and then voila, that it's been tested and verified, and we start to look at the uncertainty quantification. I think that'll start. That's happening now. I mean, these are trends that are kind of underway today. And as fast as this is moving, I'd hesitate to go out and make any forecast beyond 18 months.
What about the impacts that now people are trying to incorporate into the design of these algorithms when it has to do with biases and the application to social sciences and humanities? How do you think these developments can be informed so that these algorithms also start adhering to these emerging principles?
That is a great question. The domains that I've personally focused on have all been scientific. And I think some of the, at one level, we understand the conservation of mass and we have an equation for it. Augmenting the loss function so it comprehends the ethics. I mean, conceivably, I think you would use the same approach, but that's my simple-minded thinking. I wonder if David, do you have any thoughts on that?
Sorry, can you repeat the question? I was letting you have
essentially, if we apply some of the AI to the humanities, how do you comprehend some of the ethical implications?
Yeah, I mean, that's a huge issue. I don't think there are any easy answers. People are really struggling with that stuff, and it's getting worse over time, actually.
Yeah. AI for science is much simpler in that regard.
It is, actually. So, I mean, the training data that you use leads to biases, and then your model makes some decision. It might be controversial or dangerous or, fuzzy in the legal sense, and you have to be able to explain it. So all the same things that crop up in science crop up in the humanities, like trustworthiness and bias and stuff. But now they become like socially critical and politically sticky. So yeah, things get really, really odd when you leave the sciences. And then you got the deep fakes, right? And all those sorts of applications. So
yeah, one could conjecture, LEU, that while the commercial applications of AI had a few year head start on the AI for science, I see AI for science catching up essentially with the complexity of the models. We're seeing some scientists apply the large scale NLP models to genomics as an example. So it used to be the biggest, most complex models would only be applied to something like that interactive speech or something. And those models are now being applied to scientific problems. And no one's going to complain if we can figure out a vaccine faster, right? I mean, I'm not sure if we trust this, if we're not sure we trusted the AI model, but we got something into clinical trials faster and then the clinical trials were successful, I think you'd get a worldwide standing ovation and people would worry about uncertainty quantification sometime later. But to David's point, if you've got something else which is going to be, socially integrated, then I think so. I could see the scientific applications start to move ahead, as I think some of the applications here in the social will just might end up being stalled. But that's a great conversation over a beer.
Right, Asad.
Yeah, hi, Tom. Hi, David. Very nice summary of applications in science. One thing I noticed was common across all examples. Of course, we are seeing that in the scientific disciplines, this is becoming a trend of like including domain knowledge into the loss function or architecture, and also trying to quantify uncertainties. But by and large, all applications are still in the supervised learning regime. Whereas I think the next big thing that's coming up in the pure AI community is unsupervised and self-supervised learning techniques. I was just wondering, are you seeing the scientific community picking up on that as well? Do you know any interesting applications, or what? How do you see the future of that in science? Moving from from supervised learning domains to like unsupervised and self-supervised learning domain.
I do have some answers. I don't know if Tom wanted to jump in first or not.
Well, if you do, David, go ahead. I have a couple of thoughts.
So self-supervision is really important. I have a longer talk that I give where I cover that. The full GTC, you can look that up, my recent talk on GTC fall. So yeah, self-supervision is very important in the sciences too. And a lot of people are making use of it. Basically, anytime you want to train a model, you're better off starting from something that already knows something. If you start from scratch, you're starting from a model that knows absolutely nothing, and it's going to cost a lot of compute and time to train it. So everybody wants to start from something that knows something. And so there's a ton of different ways to use self-supervision to create a model that's kind of close to what you're looking for. So then you can fine tune it with the data you do have in a self-supervised fashion, in a supervised fashion, I mean. Most of the applications I showed actually started out with some sort of transfer learning application, either from self-supervision or from simulation. And so there are tons of different ways to accomplish that. And we could talk about that in detail if you want, about the different things people are doing.
Yeah, I would only add to David's commentary. I think most of my focus has been on self-supervision, if for no other reason that most of the community that I interact with, are coming from a comfort and confidence level in the numerical models that they use. So we want to stay as close to that kind of thought process and approach as possible. I do think and the other thing is that almost FRNN may be one of the only examples I know which kind of started from scratch, but most people are starting with an existing model and then applying transfer learning in AI for science. That's just been the normative case. Now that may change, and I could also see in the active learning sense, but again, it would probably be somewhat supervised. And that, do you have a domain, Assad, that you think unsupervised learning would be powerful?
No, I'm just wondering in general. I think like in physics, I think it's kind of relevant because if we stick to some general well-known principles in physics and then let the models learn from simulations, sort of, rather than bringing in these models trained on completely unrelated tasks, like, ImageNet or something like that. I was just wondering what would be the impact of that, and if that's at all possible, like moving into the unsupervised regime, sort of.
Yeah, so I'll repeat. I think it's not just possible, it's absolutely necessary. It's really hard to get labeled data in science. There are some cases where you're lucky, like I do, tropical cyclone detection, and then you're lucky enough that there's something called IB-TRACK's best track database already out there for you. And you can use some other tricks where like you can overlay radar data on satellite data and use one as a label for the other. So there's ways to get around it. But outside of like a few lucky coincidences, getting a lot of labels can be very, very, very difficult. In which case you just basically take simulation data or other related data and have the model train from one part of that data to itself in a self-supervised fashion. And that gets you a model that's really close. It has a lot of the important internal structure that you need, features and things. And then you can use the few pieces of labeled data you have to fine tune it, and that gives you a powerful model. But without, transfer learning of some sort, you just can't get enough data for most things. So it's really necessary.
Right. Makes sense. Yeah, I'd be interested in if you could forward some of those examples, because in the gravitational wave physics community, at least, I haven't seen it yet. So that's interesting.
Well, and that'd be a case, so, with, gravitational waves as an example, or, what happens inside the Large Hadron Collider. We don't really have a full model for some of that. So at some level, supervision, you kind of get outside, not only have a labeled data problem, you actually don't know what the constraints look like, because the standard, you're looking for data to actually inform the standard model in the first place. So yeah, they said there's,
Right.
GW is, we really don't understand dark matter. So, which is the whole reason we're trying to study it.
That's right. That's, yeah, that's interesting. But I think recently, Max Tegmark from MIT wrote a paper. I haven't read it, but they were able to relearn some of the laws of physics just by looking at the data with their models. And I wonder if you start doing this randomly and start seeing new physics come up. This is really far-fetched, but
no, it's not.
Yeah.
I mean, I think it has to happen, right?
Right.
No, I think it's really, I think you should apply for one of the AI Institute projects.
Right.
I'm serious about that, by the way. I mean, realistically, I mean, the world is your oyster if you're a researcher right now. I mean, the NSF and Department of in the United States and Europe are shifting. The funding turret is turning, and it's already started to fight. I mean, there are 2 AI institutes at the U of I. David mentioned the one that he's actually kind of a co-PI for at University of Oklahoma. And for weather, and then there's another crop science one. It's at Davis in California. So I mean, there's AI institutes, and then there's one for physics that was started at MIT. I just spoke with Jesse Thaler yesterday, and in fact, Phil Harris, who was part of your workshop last week, LU, is part of that there. So there's funding from the NSF to go explore that, and I think unsupervised learning would be a really, if I had a vote, I'd vote to fund it. So that's it's research that's certainly worth doing, and I personally I haven't seen a lot of papers in that area.
Interesting. Yeah.
All right, this is a very entertaining discussion. Just along these lines, Tom, so that we are, in the loop, we are going to be part of this. This will not be an NSF institute. I think the domains were funded in the last round, but we are now shooting for a different project, which is the Harnessing the Data Revolution program from NSF. Mm. And so, yeah, we'll certainly go and try to advance a number of domains on that project. So as we get close to the submission deadline, which is January next year, we're going to be in touch about usual business, advisory board, connections with industry, etc. Sure,
we're happy to do it. And one of the key things we wanted to do today, and somehow or another we ended right on time. I don't think I've ever seen that. Especially when David and I talk, and we both hit and we were both on time. I usually go over by 20 minutes. No, I think we should. We wanted to make sure everybody was exposed to rapids, because the question that was asked about the high level abstractions versus developing at the low level, wanted everybody to be aware these high level abstractions existed. Right? Everybody knows they exist, but that they run on top of GPUs without you having to go in and write CUDA code, because the time to science goes up dramatically just by using these tools, and they're already built off the shelf. So I want everybody to be aware of that. And some of the advances that we've made, if it's been a while since you looked at our programming stack, it's a lot easier to develop code for GPU if you need to get down to the low level. So those are the 2 things I really wanted to do. And then, this kind of the bonus round here at the end. I was happy David had time to join us today, so we could kind of walk through some of the examples of things we're seeing and hopefully pique people's interest and let them know that we're here to help, because we've generally, at some level or another, collaborated with the development of a lot of these projects, and it's NVIDIA is really keen on doing that, and we have our own research team that like to come in and see if the things that they're doing largely for the commercial environment, the transfer learning can make a play into AI for science.
All right, yeah, this is great. And if you agree, all of you, Tom, David, Zrera, and Tim, we would like to put these slides and the recording on our center's websites so that people are aware of all these tools. I am pretty sure that people have no idea that NVIDIA is producing and releasing open software for data science, honestly.
Mm-hmm.
I mean, we are very well aware of NVIDIA's reputation, but at the level of this type of tools, I think people should be aware and try to leverage them, because creating the wheel is a waste of time, resources, and energy.
Yeah, absolutely. There'd be no problem. There was nothing that was presented today, at least the guidance to the team given the presentation. There's nothing as NDA, so we'd have no problem sharing this. Sharing the slides. The only issue, it'd have to be PDF, because I know between David's slides and mine, they're probably a gigabyte of raw PowerPoint. So we had to do the PDF to get it shrunk down to size. But yeah, I don't see any problem. There'd be no problem. I want to check with Zara. Zara, there's no problem with the Rapids material, is there?
No, it's all. Actually, there's another deck that I'll share that too, that most of these slides are from the release deck, and we update them with each release. So the next blog is coming hopefully in a couple of days. And the next PowerPoint will be updated on the Rapids website too. So I'll just add a link to that as well.
Perfect. That's great. That'd be great, because people should be aware of that, because it's constantly being refined. We have updates all the time. And similarly, the SDK is being updated, a couple of times a year. And that, but I think in terms of the basic capability, what was briefed today would be good. And yeah, we'll get you. Should we just send the slides to you, LU? Okay, perfect.
Yes, please. Yeah.
Okay, we'll do that.
I was just going to say that this is Mark. So you've been, just to cheerlead a little bit, that you've been, very much engaged in particle physics. I think to mutual benefit. So, and I think what Elu mentioned, the initiative will kind of take to the next level, the partnership between academic and industry. So anyway, I just wanted to point that out, that you've been with us all along in many processes to create some of these institutes. So thank you, and I hope it's been useful for you and your.
It's fantastic. No, I mean, first of all, it's really fun. My physics professor in high school used to have this expression. He always started he goes, "Physics is fun," and he was that guy was my high school prop. He was a gas, but it is fun, and I think the particle physics is great, and it's been a very good mutual relationship. And we have things going on in other domains too. So if anything, getting exposed to David Hall and what they're doing with the climate weather community is off the rails. And we have they weren't able to join us today, but we have a similar kind of capability focused on molecular dynamics and computational chemistry. So assume what we're doing for particle physics, Mark, that you've experienced. We have similar types of endeavors, and reach out and engage us, because everybody gets a kick. We get, it's energizing, and it ultimately goes. I mean, let's face it, Jensen doesn't do this only for goodwill. It goes to the bottom line. Maybe
I'll just comment that because you touched on something about with Rapids and and I think Elia mentioned about domains reinventing some wheels. My domain has a long history in pushing the boundaries of data. And we have had a long history also in domain-specific solutions to things that are, so this is all changing. And I think there are some domains that are maybe more emergent right now. And I think that kind of lesson and that kind of approach of looking for, common solutions and solutions that exist before plowing into, small development projects is, I think, a good one.
Yeah, absolutely. We're trying to do that from the particle physics community through IRIS-HEP, Peter Elmer's project with the NSF. and some of the early projects there did leverage some of, they didn't need, I don't think they knew it was rapids, but they did. I mean, who really cares? They just happened to use, you know, the CUDA enabled NumPy, you know, the CuPy to do some work. And actually, so I mean, we're working with Jim on his, he has a proposal to the NSF to extend awkward array. So so for folks that aren't clued into this, the way the data comes off of the Large Hadron Collider isn't in a format that would fit Apache Arrow. So there's a lot of things we have to do to get it into that format. And once we get it into that format, then everybody can use rapids. So that's a simple way for me to explain it. And that's, so that's an example of the kind of thing that NVIDIA loves doing. Okay, that's great. We'll work on that, because if we can solve that problem, then everybody, you know, you just crank the data off a Large Hadron Collider. We'll use GPUs in the trigger, and the data will be out on the net, and everybody can just, you know, you can use it out there, and then just use, you know, these high level tools in Dask and not worry about it. There's a lot of work to make that happen, but that's the sort of thing we're keen on doing.
All right. Well, the conversation has been great. Thank you, Tom and friends from NVIDIA, for participating in this event. And we look forward to future engagements.
Absolutely.